Okay, good afternoon, everyone. Welcome to this month's to IEEEIS, the webinar. I hope you are very well during these days. First, many thanks for everyone to attend this month's, online seminar organized by IEEE WA chapter. My name is Hai, a senior lecturer of electrical engineering from Murdoch University, Australia. I'm currently serving as the chair of IEEEIS WA chapter. Today, it's our great honor to invite Professor Shihua Li from Southeast University, China, to give us a technical talk. At the very first beginning, I would like to briefly introduce Prof. Li for all of the audience. Professor Shihua Li was born in Pinxiang, Jiangxi Province, China in 1975. He received his bachelor, master, PhD degrees all in automatic control from Southeast University, Nanjing, China in 1995, 1998, and 2001, respectively. Since 2001, he has been with School of Automation, Southeast University, where he is currently a professor, vice dean of the School of Automation. His main research interests include modeling and nonlinear control theory, non-smooth control, sliding mode control, disturbance rejection control, adaptive control, etc., with applications to mechatronic systems, including motion control, automobile engine control, manipulator, robot, power electronic systems, etc. He serves as associate editors of many top journals. For instance, IEEE Transactions on Industrial Electronics, the National Journal of Robust and Nonlinear Control, and many other top journals. He is the chairman of IEEEIS Nanjing chapter, a member of many technical committees. He is a fellow of IEEE and IET. He has published over 200 research papers, among them over 100 international journal papers. He is one of Clarivate Analytics highly cited researchers engineering all over the world in 2017, 2019. One of the most cited Chinese researchers from elsewhere, control and system engineering, 2015 to 2019. He is a winner of best paper in IET control theory and applications 2017, a winner of annual ICI prize for best paper in the transactions of the Institute of Measurement 2016, and a winner of outstanding paper in 2019 SAM conference. The topic of today's seminar is modeling analysis and advanced control with applications for mechatronic systems. Now, let's give a warm welcome to today's guest speaker, Professor Shihua Li, to deliver the talk. Thank you, Professor Shihua.
Thank you. Yeah. So I need to share my PPT, right?
Sure. Okay.
Can you see it?
Yes, I can see that. Yeah. Thank you. Thanks.
So it's hi everyone. It's my great honor to give a speech here so I need to thank Professor Hai Wang for inviting me. Also thanks a lot for the IEEE Western Australia chapter. Yeah. So yeah, as Professor Wang introduced, I'm the chairman of the IES Nanjing chapter. So if everyone have a chance to visit China, also you're welcome to visit Nanjing. Also, since we are friends chapters, right? We need to make more chance to communicate each other, right? So my topic today is I made a little change, modeling analysis and advanced control for mechatronic systems. Yeah. So I also the director of mechatronic system control lab. So is the voice okay? The volume?
Yeah.
Okay.
Yeah.
Okay.
Thank you.
Yeah. So here's the outline. First, I will give a brief introduction of my group, MSc lab. Also, then I will give a basic introduction of disturbance observer-based control. That's the main control approach we have successfully used in many industrial projects, and I believe it's efficient and it will work well if you trust it and try it. So I will give some brief introduction of the principle and the motivation why we need to use DOBC. Then I will introduce some recent results. That's DOBC under mismatching condition. Also, I will show some application, industrial application, or some experimental verification results for the mentioned method. Okay, so we have a mechatronic system control lab. So the target why I want to have such a lab, because you know there's a gap between the control theory research and the control engineers, especially many advanced control theory. They just stay in the papers and no many chance to be successfully applied in industry or applications. I think there are many reasons. So one of the main target of our lab is to narrow the gap between control theory and applications. Because when I was a master PhD student, I don't have a chance to do research projects with company, because you know, if the problems come from the paper, it's totally different from the problems come from the industrial applications. So it take me many years to know how to do some really control projects and really successfully use nonlinear control theory. So I want to narrow the gap between control theory and applications. So we have many over 20 company projects, and so we have made some investigation on modeling and advanced control approach for mechatronic systems. So including servo control system, manipulator, and also engine control, power converter systems, and other systems. So what we are talking about today is about how to systematically model, also make some good analysis, also design an advanced controller to improve the dynamic and static control performance, especially in the presence of disturbance, uncertainties. Also, how to provide many advanced functions or features such as intelligent auto-tuning, sensorless control, resonance suppression, also fault diagnosis, and also some adaptivity to different operation conditions. So one hand is to improve the performance. Another hand is to develop some intelligent features to enhance the system, the control system. So also we have some through the company projects, we have a chance to use our advanced control method in different companies. Like Aston company is one of the top servo drive control companies, automation control company in China. Also SCI YON automation, they are listed companies, both of these. With Jingying company is an engine control company, and the Wayland company is a German company, very famous. It's about gas water heater system. So, and we have a lab. We have 7 professors, and we have many PhD and master students. So we are a big group, and it's compared to some other groups in our school of automation. So currently we have some company projects undergoing. Like for first one is the non-smooth control for servo control system. Also like for some steering wheel system, it's also servo control, and also for cladding control systems, different company. For the third one, it's the ninth project from the same company, Aston company. So we have a very long-term cooperation with some good automation companies in China. So also we have a control system, automatic docking for loading arm system, for how to design the software. Especially it's very important for the control algorithm for such systems. Also, there are many other projects and from different companies and also research institutes. Totally, we've finished over 20. So I counted. This is all the. It's about 24 companies. Some projects we didn't listed here. Some are also some for some reason. So usually, you can from the project name you can see it's all about control algorithm or control software design. Especially, we need to use different control method to enhance the system performance. So through these projects, we find a way to how to design a good controller for the industrial control system. And especially we use the method I will introduce later, DOBC, a disturbance observer-based control method. So we have made some success in this area. So this is the research platforms. You can see the AC servo system, electric bicycle system, automobile electronic system like throttle wave, fuel flow actuator, high pressure common rail fuel system, also sensorless washing machine, DC-DC converter, DC-AC inverter. So we have some good platforms in our lab, so we can have a research and development platform. So then I will give a brief introduction about the DOBC and the related method. So the original DOBC method is developed by Professor Onishi in 1980s. Also, there's a very famous Chinese professor, Professor Han, who proposed the ADRC in 1990s. Also, we have Professor Johnson. We lately find that maybe he's the earliest one who proposed unknown input observer, because this input is not control input, it's unknown input. In fact, it's disturbance. So this is another kind of disturbance observer. So also Professor She in Japan, he proposed the equivalent input disturbance estimator. Estimator is the same meaning like observer, right? So estimate the disturbance, observe the disturbance. So it's in a different form. So also another professor in UK, now he moved to a USA university, Professor Zhong, he proposed the uncertainty and the disturbance estimator. And all these approaches are linear approaches. It's easy for us to implement in the practical control systems. But later we found, because we need to handle the nonlinear model, nonlinear control system. Now in this case, you need to have a nonlinear observer. So Professor Wenhua Chen in 2000, he proposed a very famous nonlinear disturbance observer. That's the DOBC-based control method. Also, if you know the sliding mode control, know the you know, there's a very famous sliding mode control disturbance observer by Professor Xinkai Chen. Also, Professor Levent. It's called a finite time disturbance observer, which ensure the finite time convergence of the disturbance estimation. Maybe the speed of the estimation is the most fast. So also, you know, Professor Khalil is a very famous professor in USA. His book Nonlinear Systems is very famous, right? So he proposed the extended high gain state observer. So the extended state means disturbance. He treated the disturbance as an extended state. So he called extended state observer. So also he is a guy in this area. Many people don't know it. And also Professor Kim in Korea, he proposed a high order nonlinear disturbance observer and then the control method based on it. So it's a very brief survey. That I will give in the next 2 PPT pages, I will show why we need to handle the disturbance, why the PID is not enough to reject the disturbance. If you want to enhance the performance, PID is not enough to ensure the performance, especially in the presence of disturbance and uncertainty. So previous, the most early one control framework is open loop control. It means that if you can have a good modeling and system identification for the controlled plant, right? Like the plant here, if you know, if you have a system identification software, you will know the model. For example, it's a linear model, like you know the G of S, the transfer function. Then it's easy to design an open loop controller. For example, you use the inverse of the transfer function, 1 of S, GS, you can control the system well, right? So just use the inverse model of the plant model. And for the physical implementation, you need to add some low order filter to make the open loop controller physically implementable, right? So, but the design principle is very easy. You know the model, then you use the inverse model of the control to form a open loop control. You can control the system well. But if there's a disturbance, so even you have a very precise model and a very good open loop controller, it's not good because when the disturbance is strong, the system performance will be greatly degraded. So in this case, we will have to have a sensor for the output. Then we feed back the signal back into the reference part. Then we have a error, tracking error, right? So we use a feedback control like PID or linear feedback controller to suppress the error. So then if you suppress the error well, then you can suppress the disturbance well. So that's the reason why PID works well so far, right? But there's a problem. If you look back to some principle book for the automatic control, we know the feedback control is not a good control for rejecting disturbance because, you know, between the error, tracking error and the disturbance, you have a controlled plant here. If the plant dynamic is slow, then in the presence of large disturbance, it will take a long time for the error to be large error. So if we use feedback control to reject the disturbance, it's not an in-time control action because you need, when the disturbance come into the system, only in the case of large error, the control action will reject the disturbance well, because there's a slowness or slow dynamics between the controlled the disturbance and the output that's a controlled plant. So in this case, in the book, we know if we can measure the disturbance by a sensor or a device, then we have a feed-forward control action to compensate the disturbance well, right? So it's a in-time control for rejecting disturbance because I can measure the disturbance. Now in the control action, I just cancel the influence of disturbance directly. So we have a composite controller, two actions. One is feedback control, one is feed-forward control. But in most of the case, we don't have a sensor for the disturbance. We have a sensor for the output, right? So in this case, the controller goes back to just the PID or feedback control because most of case we don't have a sensor for the disturbance, right? So in this case, the main motivation is that feed-forward control is the best for rejecting disturbance. So even the disturbance is not measurable, but we know if the state is not measurable, we can have a state observer. So why don't we introduce a disturbance observer, right? To estimate the disturbance. If it can works well, and it can estimate the disturbance in a faster way, then we can still have a feed-forward compensation for rejecting the disturbance. So in this case, we can form a composite controller. We have also two parts, but we need to build a disturbance observer, right? So now we have two different control actions. We call a composite or complex the controller, not just the PID, not just feedback. We have a feed-forward for the disturbance. So the advantage is that in this case, the nominal control performance and the disturbance rejection performance can be guaranteed separately by feedback controller and feed-forward compensator. So if the disturbance can be well treated by the compensation terms here, we don't need to use the integral. Just use the PD or art feedback control here, and then we have a disturbance compensation term. So here is another explanation from the mathematical way. So we assume x1 is the position area, right? The target is to make x1 converge to 0 as fast as we can, right? So x2 is the speed. So u may be the control u may be the force or the torque, and we have disturbance. So different control task, we have different main disturbance. For example, if it's a low speed regulation, low speed servo control system, maybe the main disturbance may be the friction. There are also usually load torque disturbance, right? So also sometimes there are unmodeling uncertainties. If the system is fourth order model, you just model it as a second order. Then another second order may be the unmodeling uncertainties, right? So if for the inertia of the motor, if there are different load torques, working load, then the inertia will be time varying. So as parameter variations also may be regarded as another kind of disturbance. So it maybe come from the internal system, or maybe come from the outside, right? So we call the lumped disturbance. It may including all of I mentioned factors. So usually we have a PD controller, right? We use the position area x1 on the speed information. We have Kp and Kt to regulate the performance. But in the presence of strong disturbance, it showed the position area will not converge to 0. So in this case, we have to integral integral action, integral of x1 position error, right? But in this case, we can show it very clear which kind of disturbance can be well treated by the integral. If we assume as time goes to infinity, x1 will converge to 0. The position error will converge to 0. Then this is the double derivative, right? First order derivative. Then x1 itself will converge to 0, right? Because we assume finally we have x1 converge to 0. So the first three parts will converge to 0. For the integral item, we show you know when x1 converges to 0, this action will converge to a constant. So if we want to have this equation balanced, the disturbance will converge to a constant, or the derivative of the disturbance will converge to 0. Only in this case, the checking error will converge to 0. So if not, in another way, we say if the disturbance are not convergent to a constant, then you cannot use integral to get a enough good checking effect. Then the position error will be a bounded error. It depends on the gains, Kp, Kd, and Ki. But usually you cannot adjust the gains to be high enough because of the control saturation, because of the stability conditions, right? So in this case, the performance will be limited. You cannot enhance it if you just use an integral action for disturbance. For example, if the disturbance are periodic disturbance, the disturbance is like A sine omega t, right? As time goes to infinity, according to the frequency theory, you know x1 in the steady state, it will converge to B sine omega t. They have the same frequency, and they just you can see they just vibrate around the steady area, around the steady value. Yeah, in this case, still you cannot have a good enough performance, especially for the robot control. For many high precision control systems, it's not enough. The reason is that there's no special design for disturbance. And also in usually the normal feedback control will have a no response for rejecting the disturbance. Because there's no information for the disturbance, no modeling for the disturbance, it cannot handle the disturbance well. And a very famous feedback controller for rejecting disturbance, many people may know it. It's called a sliding mode control because they use a switching function, sine function, and a switching gain. You see, when the x2 plus cx1 bigger than 0, there's a controlled action here is minus k, and in the opposite side is plus k, right? So you will see a switching control actions between what's called the sliding surface x2 plus cx1. So for the mechatronic control system, usually it's better for using such a method because they will have a high frequency chattering for the mechatronic system, because you know around this sliding surface there will maybe high frequency switching between the minus k and the plus k. So in this case, they will cause the mechatronic system chattering. So there are many researchers working on this direction. One is to ensure the system still have strong disturbance rejection ability. Another is to reduce the chattering or remove the chattering, right? So but usually if you use the standard sliding mode control, it will cause chattering. So according to our previous discussion, the main idea is that if we can measure the disturbance, you can choose the feedback controller you like, but for the integral action, it's not good enough. You can just use a disturbance information to feed forward the compensated, right? But if the disturbance is not measurable, you can use observer to estimate, right? So in this case, we can enhance the system performance, especially the disturbance rejection ability. So if you use the PID, you can replace it with PD plus disturbance compensation. If you use sliding mode control, you can still have a sliding mode control plus feed-forward compensation, because in this case, the chattering will be largely reduced. Because the switching gate only needs to higher than the estimation error bound. In most of the case, the bound will be much lower than the bound of the disturbance itself. So the switching gate is not required to be large enough. It will cause the reduction of chattering. So our motivation is that we need to have a modeling, have an analysis on the disturbance. Then we can use feed-forward compensation design to replace the integral and to enhance the system performance. So I will show you. You say this. There are different mechatronic systems like fuel flow actuator, like winder, like AC motor, like motor pair dragging, motor bike system, manipulator. You will find that there are different kinds of disturbance. Only the step disturbance can be well treated by the integral. In other cases, like the ramp form, like the high order time varying, like the period disturbance, you cannot treat it by just the integral action. In that case, that will be a low performance. If the system you want to enhance to be a high precision control system, you have to introduce the techniques we are talking here. Yeah. So this is a very basic disturbance observer. You know, here in the inside the dash line, it's a disturbance observer. If you know the model of the controlled plant G of S, then you use the inverse of the nominal model of G of S. We call the G N of S. Then you use the inverse model. You see here we have the output. For the output, it is produced by the controlled input U, also the disturbance input U, multiplying the G of S. So if you have an inverse model here, then in the output of this frame, this box, you have the U plus disturbance, right? Then you minus U. That will be the output of disturbance. So you have a disturbance observer. So why we are adding the filter Q of S here? If the main target is to make this item, the inverse of the G of S, to physically implementable. So it's a very simple way to design a disturbance observer if the disturbance are constant, or the derivative of it converge to zero. That means it's a constant, or it will be convergent to a constant. In this case, we can prove that the transfer function from D to Y, we call the G dy here, will converge to zero if we use a Q filter, QFS, if the transfer function of it converge to 1, and the disturbance is convergent, or it will be convergent to a constant. In this case, we can asymptotically reject the disturbance. So it's a linear disturbance observer we call DOB. It's proposed by Professor Onishi. He is famous for this, and later he became IEEE fellow because of this. Then you see in the TI companies motion control solution for motor control, the DOBC method is successfully implemented in the we call the instant spin motion control motion solution. They have two basic control algorithms. One is PID, another is DOBC. Right? So it's well recognized by the industrial engineers, this kind of method. So also in some top servo driver companies from Japan, as, for example, the Panasonic, the Minus A5 servo driver. From the booklet, you can find the disturbance observer is mentioned, right? They use disturbance observer to estimate the torque, the load torque. So he shows a performance enhancement in this way, right? So about 14 years ago, we have a project with the Aston company. We successfully used the disturbance observer-based control method. We called extended state observer-based control method. Previously used PI, and also we called piecewise PI, intelligent PI in a servo driver and in the speed loop. Then we changed it as a P plus disturbance observer, P plus disturbance compensation, not PI. And now they use this in different types of the servo driver. But the problem is that they have a nonlinearity in the mechatronic or motion control systems. Previous solution is treated then as a linear one. But you see, for the n-order nonlinear systems, how to treat the nonlinearity. If you don't treat it as nonlinear, then in the according to the theory proposed by Professor Han, ADRC, or extended state observer, you see, they treat the nonlinearity as an extended state. It's called m plus 1. This is an extended state, but because for the previous order for system is n, right? From the output to the control put is n order, right? So now they add additionally order xn plus 1. Then this f dot is the derivative of the nonlinearity, or also they include the external disturbance d here. So internal nonlinearity plus external disturbance. According to the ESO, extended state observer theory, they treat this nonlinearity plus external disturbance as an extended state. Then the system becomes a linear system with lumped disturbance, right? So it will transfer the pressure to suppress the nonlinearity from the feedback to the feed-forward side. So he used an extended linear state observer, like Nuremberg observer. You see, just use the output of the original system, use the Y here. Right? It's a linear extended state observer. Then from the error equation, you can see it's very clearly. You can use beta 1 to beta m plus 1 to make the matrix A to Hurwitz stable. Then we have an additional term f dot here. If you want to make the estimation of the state, also the disturbance asymptotically stable, then we need to have the condition to sufficient condition. F dot should converge to 0. So means the external disturbance, also the internal nonlinear system, nonlinear function of state should converge to 0. Otherwise, the estimation is not accurate. So that's a big problem here. If the system have a strong stability, the f dot will not converge to 0. The nonlinear function of the state will not converge to a constant. So this is not good. So our solution is an improved one, because you cannot prove that the nonlinear states of function, they will converge to a constant. F dot will converge to 0. Usually it's not good. And in this case, if this is not satisfied, the estimation of disturbance will not be accurate, and the filter compensation will not be accurate. Maybe the performance is worse than PID if in the case of strong nonlinearity, because the f will change, will increase with the x, right? If it's a strong nonlinear function of the state. So in this case, I think the basic DOBC theory, or extended state observer-based theory, ADRC, is limited in this case, because usually they just treat the system as a linear one. So this is the basic idea is published in 1995 in Chinese journal, Control and Decision. Then 14 years later, the idea is published normally in TIE transaction. Because you see, I just list many nonlinearities we met in the project. You can see for the clutch platform, for the engine control system, we have hydraulic nonlinearity. We have nonlinear friction. We have backlash nonlinearity. We have nonlinear torque. You see, this nonlinear, the output of it changed with the state, right? Usually it's not a constant, or it will not converge to a constant. You see also in the electronic throttle system, the spring torque, in the book, we know it's linear, but you see it's a very nonlinear one. It will not converge to a constant as well. Also, in the fuel quantity actuator for the engine control system, now here hysteresis nonlinearity. It's changed with the working conditions with the state. So this kind of strong nonlinearity, they will not be convergent to a constant. If you treat them like a linear one, like a DOB and ESO, you cannot have a good estimation of the disturbance. Still, they exist. They have a bad influence in the performance, right? So in this page, we will show our motivation, our main idea. Since there are many nonlinearities in the system, you cannot ignore it. So our solution is to treat the nonlinearity into two parts. One is modeled nonlinearity, means we can use nonlinear model, nonlinear system identification technique to model it well. And for other part, it's unmodeled, as not well modeled. Then we treat it as a part of disturbance, right? It's come from the inside system. Then the outside disturbance is D1, right? We treat these two parts as lumped disturbance. And for the modeled nonlinearity, like backlash, like friction, like spring nonlinearity, like dead zone nonlinear moment, hydraulic nonlinearity, nonlinear drift, right? We can use two kinds of feedback control design. One is to cancel the nonlinearity. We use feedback linearization, use backstepping. And if maybe this nonlinearity is not a constant function, it's time varying, or it's relevant to some parameters, then we can use domination wave. That means we have a dominant function. It's changed faster than the nonlinearity to dominate it. For example, the robust control, the H infinity control, the sliding mode control, and there's such method you can use a domination way to handle the nonlinearity. The simple one is to cancel it. If you can have a precise modeling of nonlinearity, just cancel it. Another senior one is to dominate it. You use a stable nonlinear function, which changes faster than the nonlinearity, original nonlinearity. Then it's called domination, right? So in this case, either one can work well. Then you have a feed-forward design for the disturbance. Then in two sides, we can both actions can enhance the disturbance rejection ability, as well as the system performance, because we handle both two factors well. One is nonlinearity, strong nonlinearity. One is disturbance. Okay, so I will show you a recent project with the Jingning company about automobile engine control. For the we have to design advanced controller for the fuel quantity actuator. So we have a very basic step is to model the system, the linear one, the nonlinear one. You can see, I will just ignore these details. And this is their three-state system model. We have a SP called spring. We have a nonlinear spring here. You can see it's nonlinear, right? We have a friction torque, TF. You see, it's a straight-back strong nonlinear function. We have TE. T is the electron magnetic torque. Usually it's linear to the current. But now you see, it's not just the function of current I. Still, it's a function of theta. Theta is the actuator position angle. So rigorous saying, it's not linear to the current. It's a nonlinear term. You can use a nonlinear, also use the square terms to approximate it better. So there are three nonlinearities here. Then, if you don't model it as a nonlinear model, then even as it's a linear model, you have a very good linear feedback. I believe that the performance is not good enough because they exist in the system. You just model them as a linear one. So then we have a big modeling error inside of the system equation, right? So they will influence the performance. Even you use the best linear control method, you have the best parameter, control parameter, it will not work well because the nonlinearity exists in there, right? Exists there. So here, we use backstepping control to cancel the three nonlinearities. And we use the feed-forward compensation based on the ESO, extended state of observer. We have the disturbance estimation, the lumped disturbance estimation. Then we will show the result. In the case of the sudden voltage change, you see the PID is the black one. You see it will have a big overshoot, right? Then the blue one is the backstepping plus integral. That means we use a nonlinearity cancellation. That is better than PID, right? But the best one is the red line. If you use nonlinearity cancellation as well as the extended state observer based feed-forward compensation, right? You see the overshoot is the smallest one. Also, this is the control input, the duty ratio. response. You see, from it's a very it's an experimental verification result. You see the parameter variation. You see the variation value, the recovering time, the integral of abstract value of error, the performance. You see a very big improvement for the BSC plus ESO. So we handle the nonlinearity and the disturbance observer. Disturbance, the two main factors to influence the system performance well. So in this case, we can enhance the system performance. So another problem, I think it's one of the main contribution of our group, and for my IEEE fellow, the contribution is about the mismatched disturbance rejection control for the industrial control systems. I think that's our main contribution. So I will just take several minutes to introduce the problem. So it means that sometimes you have to handle the mismatched disturbance in mechatronic system. Previous one I just mentioned, the matched disturbance. What is a matched disturbance? If you are a motion control guy, you know usually we have a cascaded loop structure. We have a current loop inside. Outside is the speed loop. If it's a position control problem, we have a position control loop. Then we have an additional one. Yeah, it's in these systems, it's a cascaded structure, right? Because you have inside loop, you have outside loop. So in each loop, there's just a one order control design. In the current loop, we use the IQ star, the reference signal of the current loop. It's the output of the speed controller, right? So to control the this is there's a error. The first one, d omega dt here is for the speed loop. The second one is for the current loop, right? So for the current loop, we use the control input UQ to control the IQ to control the current. In the speed loop, we use the IQ star to control the speed. So we treat the second order control system into first order control system. So in this case, you always have U plus D. The U and the D, and they are in the same channel, in the same equation. It's called a matched disturbance. Because if it's matched, we can use just a minus D hat, the estimate of the disturbance, to just compensate in the same equation, right? But there's another way. We changed this cascaded loop into a single loop. Some motion control companies, they don't use cascaded loop, because if they want to enhance the performance, they just combine the two loops into one. We call it single loop. There's no current loop for the speed regulation system. We have only one loop. You have to use one UQ to control the two states, not two controller control two states. So in this case, you see, for the disturbance D1 here, it's not in the same channel with the control. So it's called a mismatch. Even you can estimate D1, D2 well. You can compensate D2, just have a minus D2 hat here in the UQ. But for the D1, it's not easy to compensate it directly, right? So it's called a mismatched disturbance. So in this case, there's no systematically solution, even for the LTI system, linear time invariant system. So we have some solutions for such a case for the linear one or some specially structured nonlinear system. So that's our main contribution. So in this case, you have to treat the mismatched one. Still, we need to observe it, estimate, and then the feed-forward compensation is different. So it's called a mismatched one. You see the disturbance U plus D in the matched case, but in the mismatched case, U and D are not in the same equation, in the same channel. So we have to, in this case, according to our paper, you have to introduce a specially designed KD, the compensation gain for the head. And in the general case, in the mismatched case, the KD will reduce to -1. Then it will include the matched case one, right? So the more general one is that no matter disturbance in the which equation or which channel, no matter it's different or the same with the control input, we have a way to compensate it well. So it's called a mismatched case solution. So I will not give more details on it. You can see in many mechatronic systems like PMSM, like magnet suspension system, like flight control system, like power electronic system, they always have different kinds of disturbance. And most of the time they have both matched and mismatched disturbance. So our solution is still you have disturbance observer, but you should have a specially designed KD. It's related to the ABC structure, right? And in the matched case, BU equal to BD, then you have the KD reduced to -1. Then we include the matched case. So the very earlier paper is from 2011. It's our main contribution solution from the linear case to some specially nonlinear structured system. So this also now solution for the sliding mode control for the mismatch case. I will ignore it because if you want to have a detailed one, you can see our papers. We have many extended results with some other nonlinear control methods, sliding mode control, also model predictive control, and different nonlinear control. You can use the mismatch case solution plus the feedback compensation, feedback control, and to inform different kinds of composite controller. So we have many papers on the mismatch case. And also some nonlinear sliding mode control called finite time sliding mode control solution. I just ignore it. So we have some journal papers and conference papers in this topic. We call it composite control, right? Also in the power converter systems, I just show this because the disturbance always exists, but here we have, in most of cases, we have periodic disturbance. I will show you in a fast way. Just ignore the background. You will see here we have both mismatched and matched disturbance. And in the DC-DC, maybe it's not periodic, but we have, you see some papers, relevant papers. We have a DC-AC inverter. Will show the DC-AC. So this is a DC-AC inverter. A three-phase or no matter three-phase or single phase. The states are just two states. One is current, one is voltage. Use the ratio, duty ratio to control the output, the voltage, right? If there's a DC-AC system, you will see it's matched, and also this the second one is matched periodic disturbance. Also, D1 is the mismatched periodic disturbance, because usually we have load torque variation. The load will cause the mismatch periodic disturbance because we from DC to AC voltage, right? AC voltage is periodic, so we can always find the mismatch and the matched periodic disturbance. So in this case, we cannot use the ESO and the DOB. because they are better for the constant type disturbance. For periodic disturbance, we have a harmonic observer here. So we have x1, x2, x3, x4. If we know the frequency, we use x3, x4 to estimate the periodic disturbance. Right? So x1, x2, we can have a harmonic state observer to estimate the periodic disturbance. Then we have some linear feedback control plus the disturbance. But disturbance observer is for the periodic disturbance. And another interesting example is for this is some papers for the DC-DC, DC-AC system for the power inverter system. And a very recent result is we considered multi kinds of disturbance simultaneously, because in always the system will meet different disturbance. They come together. For example, for the PMSM, we can show you we have other disturbance. Also, we have periodical disturbance caused by the Coggin torque, flux distortion, status current measurement error, node torque, or dead time effect caused by PWM. Then we can divide the disturbance into slow time varying disturbance, where we use ESO or DOB to estimate. And for the periodic disturbance, we have a harmonic disturbance observer. Then we can have a composite disturbance observer to estimate both kinds of disturbance together. So we will have a fourth order disturbance observer. The last two are for the, you should know the frequency of the disturbance, F. And the first two are for the slow time varying disturbance. So you will see in our PMSM motion control, we have, for this is a speed loop, speed controller. We have a feed-forward signal control action from the compensation for the reference signal. Then we have a feedback, which was used the proportional K. And then we have a disturbance compensation, but two kinds of action. One is for the slow time varying, one is for the periodic. So I will show, last I will show experimental verification of different. One is PID, one is just use slow time varying disturbance. Another one is use two kinds of disturbance together, right? We'll show the result. You see the speed reference is 1,500 RPM. You can see the PID, the green one, it has a bigger overshoot. And the next two, the red one is P plus ESO, just the slow time varying disturbance estimation compensation, right? The blue one is our proposed method. We have both the slow time varying and the periodical compensation handling. Then the right side is the control output, IQ star, for the control actions. Then in the 2 seconds, we add a node torque, and you can see we have a speed fluctuation. The bad one is the green, the PID, it fluctuates largely, right? The next two one, you see, since there's no difference for the next two one, right? For the P plus ESO and the P plus IMESO. But if you take a 3 second to the 3.2 second, we can amplify the diagram. You can see in the steady state, the green, the worst one is the green. It fluctuates about plus and minus 8 RPM. And for the P plus ESO, slow time varying solution, right? You have the plus minus 5 also. And for the blue one, it's about plus minus 3 RPM. The fluctuation is the the smallest one. One, if we take a spectrum diagram of the speed tracking error, you see for the 1500 RPM reference speed case, they always have a 100 Hertz, 200 Hertz, 220 Hertz periodic disturbance. For the PID and the P plus ESO, they cannot handle it. So you can see they're still there. But for the P plus IM ESO, you can see they are removed from the spectrum. So we can always have a better performance if we can treat, if we can compensate the existing disturbance. We can compensate more. We have more enhanced improvement, right? So in this case, you can see the fluctuation is just plus minus 3 RPM. It's very small one for the 1000 and 500 RPM. I think I just talked about some recent and basic principle for our method. So if there's some, I think maybe it's time for some discussion. If it's I talked much, and also if I talked too fast, maybe some listener will have some question for me, right?
All right, thank you, Professor Lee. So are you going to give some conclusion about your presentation, or?
Because I have some, maybe 1 of 3 part left, but I think it will take more time.
Okay, no worries. Yeah.
So for some enhanced, I can show in the last. We can just go to the last part. I will show some survey papers. Let me, and also our English textbook. If anyone who.
Yes, that would be great. Yeah, thank you.
Because I think if you get my point, maybe you can, you are interested, you can know some other recent papers through our survey paper, and also search our some most recent papers, and yeah.
Okay, yeah. So so no problem. Yeah. So before we go to the next round of question and answers time, I would like to give a very quick summary about Professor Lee's presentation. And during this presentation, Professor Lee has provided a very thorough overview of disturbance observer-based control methodology for our mechatronic systems. And after that, he has introduced a basic idea of disturbance observer-based control methodology. And through this slides, we have understood a lot about the basic idea of disturbance observer-based control. And third part is Professor Lee has introduced and demonstrated plenty of implementations from different industry projects. Particularly, some of the developed techniques have been successfully applied in some industrial projects. So this would be very wonderful achievements for those techniques. And now, if any audience has questions regarding any parts from this presentation, please feel free to ask. So I believe this presentation would be very helpful for all of us. Thank you.
Thank you.
Is anyone who have questions who would like to give the first question? Yeah.
Hello, Professor Lee. Can you hear me?
Yeah, I can. Yeah.
Okay. Firstly, many thanks for your comprehensive introduction of disturbance observer-based control algorithms. And I have some questions for you. The first one is, I think the thread of ADRC is to treat the system as a gray box. And so I wonder, how do you think the problem that the model-based control method will betray this philosophy? You know, because in the original theory of ADRC, the system, we don't need to know the details model of a system. But if we use some advanced observer controllers, perhaps we need to, firstly, we need to establish a relatively accuracy, model. So
Yeah.
is it betray the philosophy of ADRC?
Let me go back to the ADRC PPT file page. If you can, let me wait a moment. If you can you see? I just need. Can you see the page?
Yes,
no?
we can see that. Yeah.
Yes.
You see the ADRC? No. Let me see. Check to the. I think.
Now we can only see the book and survey papers page. Yeah.
Sorry. Need to quit. You see?
Yes, we can do that. Yeah.
Yeah. Still, for ESO, they need to know the model, but usually they will treat other part of the model as a part of lumped disturbance. Sorry. You see, they will treat other part of the system as a part of lumped disturbance. And for the DOB, we think it's better because they will treat the nominal model well. So if there's some linear part from the f of x and d, then you know the linear part of it. Then still the nominal model should be more precise than the ADRC one. Because the ADRC also they need to know the model. You need to know the B. You see the parameter, the gain before the U. Also, it's in the motion control system. It's inertial. You need a system identification for the inertial, right? But still, it need to system identification. The simple one is that they always treat the second order system as a second order integral. But if this, for DOBC, for DOB, if you know it's not just second order, it's you can have more precise information. Then the disturbance observer should have a more accurate estimate for the disturbance, because the model information, we use a better model information. But if just from the mechanism, just second order, you don't have a system identification technique. You just treat it as a second order. Maybe you will try ESO, but you have a system identification method. You have a system model, well built system model. Why you don't use DOB? DOB, we have a G of S, not just second order integral. Most of the case, they are not just a standard form. So even for the linear case, I think it's better to use more system identification to have a more precise model. not just a second integral, right? Because in that case, you will put more information to the numped disturbance. But for such information, you can have accurate information. You just ignore it. You just put them into the part of numped disturbance. It will give a higher pressure for disturbance estimation. Because each disturbance observer have limited function. They cannot estimate everything. Right? That's my answer. Is it
Yes,
okay?
yes. Yes, that's a good answer. And I have another question, also about ADRC. To the best of my knowledge, the F dot, the condition for the F dot is upper bounded, but you mentioned that the F dot need to converge to a constant.
A rigorous saying is not bounded. Consider an example. If the fx is the x with the power of 3, you see, x with the power of 3. Now you see, if you take f dot, it will x squared. It will not converge to any constant, or it's not bounded, because it will increase with the state, right? If it's a local stable system, it will as the states increase, it will cause the system unstable. So for the case of strong nonlinearity, you cannot assume that it is bounded. If the f of xd if it's just external disturbance, you can call it bounded because it's from the external. But if it's a part of some part is a function of state. As the state increase, they will increase. And if it's nonlinear, strong nonlinear, it's better than it's faster, much faster than the linear one. So you cannot call they are bounded. So in some papers, the people assume it's bounded. If you call it numped disturbance including external function of state, then they will be rejected by the mathematical guys because it's not rigorous. Just as I mentioned, there are many examples, they are not bounded. So that's the way, if you want to have a good paper, you cannot assume f dot is bounded.
Yes, right. If we model some, if we have a
if you model
x
with the power of 3, then you sometimes if you assume the modeling error is bounded, maybe it's acceptable. Even the modeling error plus the external disturbance as a lumped disturbance, then maybe it's acceptable because you most of the time you have accurate cancellation of the nonlinearity.
Yes.
Hi.
That's all my question. Thanks for your answer. Okay.
Hi, Professor Shuha. It's my name is Farad from Paris and Murdoch University. Thank you very much for the very good presentation. I have a question about the application of your system in power electronic applications. So you showed some very interesting, even practical examples that you have used your state observer and extended state observer in controlling that. My question is mainly, when you're doing this practical experiment, how do you create or impose that disturbance to the practical setup? So what are how do you create that disturbances which later your controller tries to respond to that properly?
You mean for the experimental result, how to create a periodic disturbance?
That's right, yeah.
But usually they exist in the system. They exist, for example, the DC-AC, because you need to, the output is the AC voltage, right? It's periodical. It's periodical. Then if you make some the load variation, you see the load variation, then you will cause the variation of the voltage. Because it's AC voltage, then the periodical, then the disturbance should be periodic.
Right. So it's actually mainly by changing the load value that
Suddenly some load variation or some sudden load change.
Right. Okay. Yeah. Very good. Thank you very much. Thank you.
Thank you.
So do we have any more questions from the audience? I think now our session is very active.
Thank you. Yeah, I hope it will be helpful for, especially if you are the freshman, maybe you can take a look at our survey paper. You see, it's close to 1,000 citation times. The first author is Professor Wen Huachen, who proposed the nonlinear disturbance observer in 2004. Yeah, right. And I think it's a very good survey paper. If you know, have some idea about H infinity, robust control, and adaptive control, and also output regulation, and many other good methods. Also in repetitive control, iterative learning control. All these methods are efficient for rejecting disturbance, but they are different. For example, the adaptive control is good for rejecting the parameter variation. And also H infinity is good for the rejecting some vanish disturbance. But in this survey paper, we show they are efficient for different case. They have a different way to reject the disturbance. I think all these methods, they are good. They are better than PID, and each method has its limitation. I think I suggest if any of you have a chance to try, you can try DOBC first.
Sure. Yeah. Thanks very much for Prof. Lee's good recommendations. Later after this session, definitely we will download this survey paper and upload to our IEEE online website. And if anyone who has interest in this survey paper, please feel free to download. And I have one question for Prof. Lee. And as you mentioned, you have introduced, many PID control methodology for the comparison purpose. And have you considered any computational intelligence-based PID control methodology for the real-time implementation? I think by using the computational intelligence-based PID control methodology, the control performance can be greatly improved. So how to compare these improved PID control methods?
What do you mean about the intelligent PID or intelligent control? The expert PID or some fuzzy logical.
Yes.
Yeah. I think the company guys before our DOBC method, they use intelligent control PID because for each type of servo drive, they find a good formulation of the time varying PID. They change according to the area, according to some working conditions. Yes. They are piecewise and they have some rules. So they works well before our method. So they refuse, the control engineer refuse to change their method to our DOBC. But we have a very big performance improvement. So their boss, they force them to accept it, and then later they have to accept it. Right? Okay. And I think because it's not easy for other guys to accept or extend the result. If you just use the expert experiments, it need some intuition, need hard work, and maybe some many other things. And it's not a good way for our to do research because for the students, it's not easy for them to just for example, the 1 year project, we need to enhance the performance largely, Otherwise, some company boss will not support us. So in this case, it's not easy to transfer the experience to some new freshman. So, but for our DOBC on the nonlinear control framework, it's easy to understand if you are good in math in theory, and you just need to do some simulation and know the parameter tuning rules. And I think you can work well. It's always better than PID, and also So it's also including the nonlinearity modeling and the cancellation. I think most of cases, both strategies work well, and combine these two guys together, it should be better than the intelligent PID. But for the intelligent control, we use a neural network to model the friction, because the friction, you see, very strong nonlinear. If you use neural network, it can identify it better.
Yes,
but it's offline identification if the friction model is fixed, and I think the performance is always better than the conventional nonlinear identification.
Sure. Yeah, that's great. Yeah, thank you very much, Prof. Do we have any more questions from the audience?
Yes, I have one question. Hello, Prof. Lee. I'm Amir from Murdoch University. I'm the highest colleague. Thank you very much for your interesting presentation. I have two questions. First is a sort of philosophical questions, okay? And then one is more technical one. So I start with the first one. Even though there is a very, significant effort and, too many research papers on the nonlinear control, better than me, still, maybe 80–90% of the companies using the PID in reality, in the practice. So I want to know your perspective. Is there any transition from this, old age classic controller, or these are enough for the purpose we have in the future? This is my first question.
I think, I think there is maybe some misunderstanding in this data. For 80 or 85%, it's usually we call it PID, but it's for the engineer controller. They don't have a very rigorous consideration of PID. For the motion control guy, we know you always will use the friction compensation to reject the friction or to cancel the friction. You notice that in the Panasonic servo driver, I showed there also in the third term is about the friction load torque of friction compensation. That means in the practical case, if even you use PID, for the low speed working condition, usually we have PID plus friction compensation. So in this case, it's called nonlinear control, not PID. But previously, many people count it as a PID. They count this enhanced PID. But from the mathematical way, you see that for the control input, you always have a minus F. Minus F is the friction plus PID. Now, in this case, we should regard them as nonlinear control, not PID. So in many of cases, for the motion control guy, if they use friction compensation, if they use backlash compensation, if you use some functions, such function, you should treat it as a nonlinear control. So I think in motion control theory and motion control area, most of the PID maybe they are nonlinear, not PID.
Okay, thank you.
If you take a look at from this viewpoint, maybe I will believe that I think if people can count it in such a way, maybe the percentage will be lower. And I think more and more nonlinear control method should be successfully more successful, because in the future, the performance in enhancement should be a forever topic. And we need to have a more comfortable life for robot control. For many control systems, we always need a higher and higher performance. Then in this case, the sensor will be more accurate. The controller should be more accurate. So in this case, PID is not enough.
Okay,
that's
thank
my
you.
answer.
Yeah, thank you very much for your comprehensive answer. My second question is more technical on the your design side. My question is that how do you involve the constraints we have on the input, for example, of the system control input in your design? For example, there is from the physical point of view of any actuators, for example, servos or control valve, or for example, DC motor, we cannot apply, for example, more than the for example, force or voltage to the motor. So, but from the point of the nonlinear system design, I want to see how you involve this mathematically, in your formulation, or you just saying that, okay, this is just a sort of trial error. You adjust the, the input control so that you don't, pass the constraint. So this is my second question.
Yeah. It's a very good question. So you are talking about the control saturation, right?
Yes.
Yeah. One case is that we cannot, in most of the company projects, we cannot change the hardware. The Aston servo driver company, every year they sell about 1,000 servo driver, 100,000 servo drivers every year. So it's very difficult for them to change the hardware because they produce a lot of them. You cannot say you just change the hardware in words. They will say it will cost much price for us to change the hardware, right? So in this case, the control saturation is fixed. You have to in this case, all the control algorithms they have fair comparison because we have the same control saturation. But most of case, if you have the we call it input shaping, we change the step reference into a soft one. We shaped them like tracking a curve, not a step reference. Then we can avoid, most of case we can avoid control saturation, because only in the large area case, large disturbance torque case, we will have the control saturation. Because for the general servo driver, they need to adapt to different working conditions. If the gain is not large enough, it's just the control saturation just come in the first stage where the area is big. Most of the working case, like the manufacturing working, the speed is maybe, for example, working in a constant reference speed. Then the system working in the steady state. The control saturation in this case is not a big problem, because only in the starting stage the area is big. Then maybe the control put in bid is big. But I do recognize there are some cases they always, if you need to have a big area, big load torque, maybe you will meet the control input saturation. So in this case, if the saturation have a big influence for the control closed loop system, maybe we can suggest the designer in the next circle of the whole system design, you should add the control energy. You should add the hardware output. You should add the control torque. In this case, we can have a more big advantage for the nonlinear control to the PID, because for the Chinese martial art, if the guy is a good martial art player, and it will fight with a general guy, right? But if you have a playground, it can defeat them very easily. But if you put these two guys in a very small room, they just hack together, you cannot use your martial art. So if the control input, the hardware is bad, it's the very limited control input. The nonlinear control, maybe sometimes they will not have enough good advantage for the linear part because of the controller situation. If you always, in the working condition, you always meet the control situation, then everything is the same. For example, the open loop, the PID, the nonlinear control, if they are in saturation, most of the time, half of the time in saturation, then there's no difference. But outside of control saturation stage, the nonlinear control one should be better than the PID. So the advantage depends on the control saturation status. If it lasts long, maybe there's little difference. So in this way, we should suggest the design to have a good enough hardware to show that then we can have a good and place for the control algorithm to show its potential and show every better one.
Thank you very much.
That's my answer.
Yeah, thank you very much for your answer.
Thank you, Prof. Lee. Do we have any more questions from the audience?
Hello, Professor Lee. I have a question about your method. In our system, we have it is a servo control system. Our motor have a very poor performance. If you give a small input, the motor drive cannot detect it, and so the motor cannot act. So, do you have some? I mean, if we think this kind of problem as uncertainty, so we do you have some good method to tackle this uncertainty? Use the DOB.
Yeah, but the first thing is not to use some nonlinear control. The first thing is you have to perform a system analysis. Means you have to connect the data. You have to see your model. You have to show some, also consider the influence of noise. You have to model your system well. If you just use PID and your hardware is not changed, or you do not have a hardware solution to improve it, you just need, you can only do is to use control algorithm. Then I suggest you first you need to model the system. It's a one order or second order system, and what is the parameter goes to. You need to system identification. Then if the identified model is accurate, maybe you can try some model-based control method, and like ADRC, DOBC, and also any other model-based control method. But if you do not model it, you can't do control designer, because most of the case they are model-based. So I suggest first you need to do the model to have a good precise model. Then you can try the method. And for the model, first easy one is to do a linear system model identification, right? But if you want to enhance the node speed, you have to add the friction. If it's all for the high speed, the friction is not a big one. Maybe you need to consider the node torque, to have the node torque estimator to consider the node torque. And if there are some, backlash, maybe the step response, for you can see the speed, they will increase, and in the middle stage they will decrease, then they will increase. maybe you will find backlash in the test. Then you should consider backlash. So it's different according to the machine, but you should put much time in system analysis and do some modeling. If you can have a good knowledge of the system, then you can find when to handle it. That means why we need to find a doctor, because we need to find the reason why we are sick.
Yes.
Yeah.
Actually, we use the PID. It also don't get a very good performance. So we need, as you say, we need to modeling the uncertainty precisely first. I think it's very important.
Yeah. You can try, but if you have any problem, you can contact me. You're welcome.
Okay. My signal connecting not very good. Okay.
All right.
It's okay. It's okay. Okay.
All right. So thanks for Prof. Lee's, the detailed explanations for those questions. So because of the limited time, so we don't want to, take too much time from, Prof. Lee. And many thanks again for Prof. Lee's wonderful presentations today. And we all, learned a lot. We all enjoyed a lot from these, wonderful presentations in terms of the theory, application, as well as the the industrial experience. And we would like to express our sincere gratitude to Prof. Lee's wonderful presentation, and as well as time and effort today. And before I conclude today's presentation and webinar, I would like to say a few words. So first of all, many thanks again for Prof. Shihua Li's wonderful presentations, and because Prof. Lee is the serving as the chairman of the IEEE-IS Nanjing chapter, so possibly in the future we would like to have more exchanging activities between Nanjing chapter and WA chapter. So because Nanjing chapter, I know, is one of the most active chapters in China, so possibly it's better for us to arrange a few exchanging activities between two chapters. So this is one vision I would like to say. And secondly, we would also very like to invite Professor Lee coming to Perth for delivering a face-to-face talk in seminars or conferences to be organized or co-sponsored by IES chapter in the next few years. As everybody knows,
that will be my great pleasure. Maybe we can also drink some Australia wine.
Yeah, definitely. Yeah. And as everybody knows, our colleague, Dr. Fahad, as the IEEE session chair, has been arranging a few international conferences in the next few years, and we, as the the IEEE-IS chapter, as one of the co-sponsors for those conferences. And for us, we are still planning to organizing a few international conferences, particularly focusing on control systems and technology. So in the future, we would like to invite Professor Lee coming to Perth for delivering talks, as well as to have some good sightseeing for Perth, because Perth has a different sightseeing compared to Melbourne and Sydney in Australia. So lastly, I would like to say I would like to look forward to everybody in our next month's webinar, and have a good lovely weekend for the audience from China, and having National Day in the next week. And for the audience from Australia, particularly from WA, have a lovely weekend and happy Queen's Birthday holiday in next Monday. So thanks again for Professor Lee's wonderful presentations today. So thank you.
Yeah.
See you next time.
Nice weekend. See you guys. Bye.